Okay, so we are going to start looking at the next outcome now, right? So, we were working on with solutions, and now we're going to look at solutions, acids, and bases. So this is going to be outcome C2. Um, so moving on to something a little different, but there definitely is a lot of similarities between the solution stuff and the acid-base stuff. So first thing we're going to start by doing is just reviewing some of those properties that we associate with acid and bases. So this table should look relatively familiar to you because you did see this last year when you were in Science 10 and you looked at some chemistry, right? So we talked about a bunch of different tests, and then we kind of talked about how acids would respond and how bases would respond. Okay, so first test is litmus paper, right? So remember there's red and blue litmus paper. So when we dip red into an acid, it stays red, but when we put blue paper in, it turns red. So when we see that blue paper turns red, that's a positive test for an acid. When we're looking at bases, the blue is going to stay blue, but the red is going to turn blue. So if we see that red paper turns blue, then we can confirm that something is a base. So the one thing to point out is we also obviously have neutral solutions, right? And right now this table just has acids and bases. But if you think about a neutral solution, if I dip blue paper in it, it's going to stay blue. And if I dip red paper, it's going to stay red. So anytime you see that the paper doesn't change colors, that doesn't actually really tell you what something is. So let's say I dipped like red paper into the solution, it stayed red. I couldn't then say it has to be an acid. I could say it's not a base, but the only way that I could confirm that it was an acid is to then test it with blue paper and see does it turn red. If it does, it's an acid, but if it doesn't, then that means it's just going to be a neutral ionic compound, okay? Next test is going to be your pH paper, right? So when we use pH paper, it's a little strip of paper, we dip it into the solution, and then usually we have a little like color chart, and we'll see that every single number has a different color associated with it. So if it has a pH of 1, it's one color, a pH of 2, it's a different color. So we literally dip it in, we match it up, we figure out what number it is. So when we're talking the pH scale, right, 7 means neutral. So if I dipped it in and I saw 7, I would know that it was a neutral solution. But if I saw it was less than 7, I would be able to decide it was an acid, and if it was greater than 7, I could decide it was a base. Okay, the other type of test that we can do is reaction with an active metal. So you would have done this last year in Science 10, where you kind of did that acid-base lab. You took the little strips of metal, remember you put it into the test tube, and then you kind of capped it with your thumb, and then you waited a little bit of time, and then you took like that lit splint and put it over top, and it made that high-pitched popping noise. And that's going to be your positive test for an acid. So when we put one of those active metals like magnesium or zinc into an acid, it's going to bubble making hydrogen gas. And we can test for hydrogen gas using that splint test where we get that high-pitched pop. What we find is if we put one of those metals with a base, there are no bubbles. So the test with these metals is literally bubbles or no bubbles. I see bubbles, it's an acid. I see no bubbles, it's either a base or it's some type of neutral solution. Okay, next test is conductivity. We talked about this in the solutions unit, right? We talked about solutions as either being electrolytes or non-electrolytes. And we said for something to be an electrolyte and to be able to conduct that electric current, it has to have ions present in solution. So we find acids undergo ionization when we put them into solution, right? We talked about that also back in the solutions unit. So they will conduct because they have ions. Bases, for right now, all contain hydroxide, which makes them an ionic compound. So they are going to dissociate in solution and produce ions, so they're also going to conduct. So when we think about conductivity, it's really only helpful to identify those molecular solutions, right? Back in bonding, remember we talked about conductivity. We said moleculars never conduct because they don't produce ions. So conductivity is probably, I would say, the least helpful of all the tests because it's really only going to tell me if something is molecular. It's not going to tell me if something is ionic or something is a base or something is an acid. Okay, taste. Obviously, if we were in the lab, we wouldn't start tasting chemicals, but there are many chemicals that you have at home that are I don't want to say not chemicals, they are chemicals, but they're like everyday cooking things, right? So acids taste sour, right? Think about vinegar, right? You have vinegar at home, that tastes sour. You think about lemon juice, that tastes sour. Those are all acids. And bases have like a bitter taste, right? So like a common base you would have at home would be baking soda. Not that I'm saying to go put baking soda and see what it tastes like. It doesn't taste very good, but it tastes bitter, okay? And then the last test we tend to talk about is feel, right? So like if you were to get some on your hands, when it's in a solution, how's it going to feel? So with acids, there's not really a special feel. It literally just feels like you have water on your hands, right? So your hands are wet. A base is going to feel slippery, right? So normally you'll be like, you rub your fingers and it's like, oh, they're sliding on each other a lot faster, right? And so that can tell you that you have a base on your hands, right? So helpful if you're in the lab, because then it's like, oh, my fingers feel really slippery. I know I've gotten chemicals on them. I better go wash them off. The acid is a little trickier because you're not going to know that it's acid. You might just think it's water, but that's where generally you want to make sure that your hands stay nice and dry. Okay, so these tests are important. We use them even in Chem 30. There's usually a really straightforward question on the diploma that's kind of just like, oh, you have this unknown compound. When you add a metal to it, it bubbles. It turns blue litmus paper red, and then they'll give you like 4 options and be like, what chemical could it be? And from those observations, you need to decide that it's going to be an acid. And so then you'd look at your chemicals and be like, oh, well, this is a base, so it's not that. This is molecular, so it's not that. This is neutral, so it's not that. And then be like, oh, here's my acid. I'm choosing that one. So when it comes to acids and bases in solution, right, we kind of already talked about this before, but both are going to conduct electricity. And that's because they both have ions in that solution, and they are both electrolytes. So when you think about the equations that we've written, right, we kind of have 2 equations here. We have one for an acid, and then we have one for a base. So what you find is here we have HCl. That's our acid, right? And remember we talked about how acids undergo ionization. Okay, then we have sodium hydroxide. That has that hydroxide, so it's a base. This undergoes dissociation, okay? So when we were looking at writing out these equations before, just move that up a bit, the one thing that we also included in here, I can't really do it super well on here, right, was we would put water over that arrow to indicate that it had been placed into solution. And then with that acid, usually we just included the water in the equation, but you're going to see as we talk more about acids, we're going to start to change that up a little bit, okay? So we go through a couple of different definitions of acids and bases. This right here is basically your first set of them. So Arrhenius was the first one who kind of came along and gave us a working definition of what acids and bases are. So Arrhenius proposed that acids contained hydrogen atoms that formed hydrogen ions in solution, right? And that's why we've always said when we're looking for acids, well, that was a horrible circle, that we are looking for this H part right here, right? And then here's that hydrogen ion that we were able to form. So Arrhenius proposed that bases contained hydroxide ions, right? So here's our hydroxide ion, and that they're going to dissociate in solution to produce that hydroxide. So acids have hydrogen, and they're going to produce these hydrogen ions. Bases have hydroxide, and they are going to produce hydroxide ions, okay? So first working definition of acids and bases. Acids have H, they produce H+. Bases have OH, they produce OH- ions. And so that was kind of our first working definition that we used for acids and bases, okay? So when we look at this slide, this is more or less just talking more about what I already talked about, so I guess we will skip that slide and move to the next one. So we do have some problems with the Arrhenius theory, though. There are a couple of issues, and some of them are a little more obvious than others. And one of those is we have some things that we know are bases. And we know they're bases because when we think about those tests that we talked about at the beginning, right, these ones here, We see that they turn the red litmus paper blue. We see that if we check their pH, it's higher than 7, right? We can see that they feel slippery, like they meet all those requirements. But when we look at the formula, right, so ammonia is a classic example of that, right? I look at that, I wouldn't be like, that's a base, right? If anything, I would look at ammonia and I'd be like, I guess it could be an acid. It has some hydrogens in it. But when we actually test it in solution, it is definitely a base. It usually comes in with a pH right around 9. So that means the Arrhenius theory isn't really working. It's not actually explaining it, right? Because this doesn't have hydroxide in it. So this is where they came up with a modified theory. Okay, so this modified Arrhenius theory recognizes that there's another way that something can be a base. Okay, the other way that something can be a base is that it reacts with water, right? If you think about water, although we write it as H2O, the other way we could write it is as HOH, right? And if I were to go to water and I were to remove this hydrogen, I would be left with hydroxide. So that's actually what we find happens with ammonia. When that ammonia goes into water, it takes a hydrogen away from water and it produces this ammonium ion over here and that hydroxide ion. Okay, how it does that, if you think back to when we did bonding, right? Remember ammonia, if we drew out that Lewis dot diagram, it looked kind of like this with those H's. So what happens is we have that lone pair up on top of that nitrogen. Remember we talked about that special type of covalent bond, of coordinate covalent bond, where something would just come in and latch on to here. So what happens is this hydrogen from water comes over here and takes up that position, right? And as that happens, we produce the ammonium ion because now we have an additional hydrogen in place, right? So if we put that in, we get this, another hydrogen here, and then the last one over on that other side where this has a charge, right? Remember when we're drawing charge things, we use square brackets and we put that plus up here. And then our other product that we're left with is that hydroxide ion, which now has a negative charge because it lost a positively charged proton. Okay, so we're not going to ask you to like draw it out like this, but just kind of showing you what happened. So ammonia falls into this general category that we tend to call a non-classic base. Okay, when we talk about classic bases, those are the ones that kind of match up with Arrhenius's original theory, which is that they contain hydroxide. Non-classical bases work up into what we call the modified Arrhenius theory. And the modified Arrhenius theory recognizes that there are some compounds that are able to produce hydroxide. So producing hydroxide is kind of what makes something a base, is that it has the ability to produce hydroxide. The question is more, how does it do that? So in a regular base, which has hydroxide, it just dissociates and breaks apart to give me that hydroxide. But in the case of ammonia or a non-classic base, they have to actually react with the water, take a proton away from water, and produce that hydroxide. So there's kind of 3 non-classic bases that you should be aware of in Chem 30. Okay, they are ammonia, they are sodium carbonate, and sodium hydrogen carbonate, right? Which would be your baking soda that you have at home. So the ammonia reacts with water, and these other 2 do the same thing. The only difference that we have with these 2 is they undergo a dissociation first, right? So if we think about sodium carbonate, and we place that in water, right? This is going to first start by dissociating, and it's going to give us 2 sodium ions and that carbonate ion. Okay, if you remember, we talked before about how there's that acid-base table at the back of your booklet. You will find that that carbonate ion is in that table, kind of close to the bottom in the base column. So when I look at this, it's this carbonate ion that I care about. And the reason I care about it is this -2 charge. Okay, because it has that, that means it has the ability to accept 2 protons. So when we look at these non-classic bases, in the case of sodium carbonate and sodium hydrogen carbonate, there's actually a couple reactions that happen. The first one is going to be to dissociate it, right? Which is what we just did. The next thing is to recognize what part of it is the base, which in this case is the part with the negative charge, and that's because hydrogen has a positive charge. And then what we find is that that carbonate ion is going to react with water. And it's going to do the same thing that it did when we reacted it with the ammonia up there. It's going to take a hydrogen away. And so we're going to make hydrogen carbonate and a hydroxide. Oh, I don't know what I just did there. And a hydroxide. Okay, and then this technically could do another reaction because it has a negative charge, but we'll get into that a little bit more in another lesson where we look at some other things and get into a little bit more complexity, okay? But for sodium carbonate, sodium hydrogen carbonate, we need to dissociate first, find the part with the negative, and then we're going to react that with water to actually be able to produce that hydroxide ion, okay? So that's the first limitation, that it doesn't explain all of our bases. But there is a second limitation as well. So the second limitation is that hydrogen ions don't actually exist. Instead, what we find is that we get what is known as a hydronium ion. Okay, and the reason we get that, again, kind of gets explained by the most part by looking at some dot diagrams, right? So if we think about water, we have our oxygen, it has that full valence shell because it also has 2 hydrogens. Okay, if we then have an acid in the solution, that acid is going to produce those hydrogen ions. So when you look at that hydrogen ion, it doesn't have any valence electrons right now, but we know that hydrogen wants 2 valence electrons. You look at oxygen over here, it's got 2 electrons here and 2 electrons here. So this hydrogen is going to come along and say, hey, let's share. And it's going to tack itself into one of those spots. Okay, it could go here, could go there, it doesn't matter. It's going to go to one of those 2. And then what we wind up producing is hydronium, which is written as H3O+, and that's because now we have this, and we're going to have those 3 hydrogens. Okay, and that's going to go down here, or again, you could have put in 1 over here, but we're going to wind up with 3 hydrogens in our square brackets with that plus charge. Ooh, that didn't do what I wanted that to do at all. Oh, I undid too far. Okay, but yeah, we wind up with this with a plus charge. So that's our other limitation of that Arrhenius theory, right? It said acids have H, which is still totally true, but then it said that they produce hydrogen ions. Now we know that hydrogen ions don't actually exist. Instead, it's hydronium. This is why you'll remember when we first started looking at ionization, I wanted you to include that water in your equation, right? And we didn't do that with regular ionics. But here, you'll notice we included that water, and that's because when we break this HCl apart, the H is going to get added on to this water to make hydronium, and that chloride is going to become its own ion over here, okay? So we modified what a base was, right? If we think about bases, the original definition of a base was they have hydroxide, they produce hydroxide. We modified that to create the modified Arrhenius, which said that bases either dissociate or react with water to produce hydroxide. So that kind of covers both of those bases. When we look at the Arrhenius acid, we're going to modify that one to say that yes, acids contain hydrogen, but they produce hydronium ions in solution, okay? So important to make sure you read a question carefully to see if it's asking you to use the original Arrhenius or the modified Arrhenius, right? Because the original Arrhenius, although it explains probably 80% of things, it doesn't correctly identify 20%. The modified theory, though, kind of accounts for a lot of those things that the original Arrhenius would not have predicted correctly. So your acids don't really change. You're still usually able to predict your acids the exact same way. It's just your bases where you kind of at this stage have to make sure you're familiar with those 3 additional ones of ammonia, sodium carbonate, and sodium hydrogen carbonate. Okay, so this slide kind of just gives you that specific theory so that you know what it is you are looking for. Okay, there's one other, or I guess 2 other. Okay, so there are just 2 other kind of weird exceptions that you need to know of as well. We don't talk about them too much, but they are things you should be aware of. And those are our oxides, okay? So oxides are compounds that contain oxygen. We classify them into 2 categories, non-metallic oxides and metallic oxides. So a non-metallic oxide would be a compound that contains a non-metal with oxygen. So carbon dioxide is kind of your classic example of that, right? Because carbon is a non-metal, it's paired with oxygen. So what we find for our oxides is that they undergo formation reactions, right? So this is a formation reaction, okay? It's not like the true definition, which is an element plus an element to give us a compound, but it is a formation in that we have 2 things joining together to create one, right? So if I combine CO2 with H2O, I'm going to make H2CO3. And that's carbonic acid. So what I need to recognize is that non-metallic oxides form acids when we place them into solution, right? And as soon as I form that carbonic acid, it's going to be able to ionize in the water and produce hydronium and that hydrogen carbonate ion. If I look at metallic oxides, they're a little bit different. So these obviously contain a metal with oxygen. So here I have sodium oxide. It also undergoes a formation reaction with water. But this is going to produce sodium hydroxide. So what we find is that metallic oxides form bases, okay? Whereas those non-metallic ones form acids. So we're not going to ask you crazy questions about those, but do be aware that there are some oxides that are acids and bases. Even though if I looked at CO2, I'd be like, it's nothing, it's neutral, it's molecular, it's a nothing, right? And if I looked at Na2O, I'd probably be like, well, that's a neutral ionic compound. There's no OH in it. But these are a little tricky in that they do undergo those formation reactions to be able to produce that, okay? So that's kind of your intro to acids and bases, kind of walks you through what you're looking for, what those initial definitions are, and what some of those qualitative properties are, so that if you were asked to identify an unknown, you'd be able to do that based off of those different properties we talked about.